Hi. In this session, we will learn about the effect of change of origin and scale of moments. That means, if we change the origin as well as the scale of the deviations, then what will be the effect on the moments? Let's start with the change of origin. These numbers are not mere numbers, but the deviations from the origin 0. So, 2 is actually 2 minus 0. So, it's a deviation from the origin 0. Likewise, the 7 minus 0 is also a deviation. Now, look at this figure. Here the origin is 0. So, 2 is actually a deviation from the origin 0. So, this is the deviation here, right? Similarly, the 7's deviation is here. The deviation of 3, the deviation of 4, the deviation of 9 and deviation of 8, right? Now, if we change the origin 0 to any arbitrary point A, then the deviations will look like this. 2 minus A, 7 minus A, 3 minus A, like that. That means you are replacing this 0 with some arbitrary point A. Let us suppose that the arbitrary point A is 5. So, the deviation of 2 will be looking like this, and it will be on the left hand side of this arbitrary point. You see the deviation of 7, it is on the right hand side of this arbitrary point A. This is the 3's deviation, this is the 4's deviation, this is the 9's deviation, and this is the 8's deviation. So you see that the deviations are sometimes on the left hand side and sometimes on the right hand side of this arbitrary point. Now we move to change of scale. How will you change the scale of deviations? If you divide the deviations by some number h, which is not equal to 1, then you will have a change in scale. Say this side, the unit is meter. Now this tree is standing at the 0th location. This gentleman is standing at the 3rd location. That means this gentleman is actually 3 meters away from the tree, right? So the deviation will look like this. This lady is standing 7 meters away from the tree. So this is the deviation. Clear? Then what will be the mean of these two deviations? It will go like this. 7 minus 0 is the deviation of this lady, and 3 minus 0 is the deviation of this gentleman. So you add these two deviations, divide the sum by 2, and you will get 5. So 5 is the mean deviation of these two people, right? Now, if we divide this meter, this scale, by 1000, then this scale will become kilometer, isn't it? In this situation, can you say that this gentleman is still having a deviation of 3 from the tree? Or this lady is still having a deviation of 7 from the tree? I hope not. Because this meter has been scaled down by dividing by 1000. And this is equivalent to kilometer. So this scale is now in kilometers, not in meters. So to get the mean deviation now in this situation, you have to go like this. You have the original deviation 7 minus 0 and you divide that deviation by 1000. Same thing you go with this deviation also. Now you add these two and divide the sum by 2 and you get 0.005, somewhere here, very close to 0. So what did you see? Previously, the mean was here at 5, remember? And now it has gone down to 0.005. So if you change the scale, then the mean deviation, which is the moment of order 1, is also getting changed, right? So we have like this. This is the original deviation, that is 2 minus a, and you divide this deviation by h. And this h is actually 1000 in our example, right? You do this to all other deviations like this. We call this scaled deviation as U1. Similarly, U2, U3, U4, U5 and U6. So we can write like this, Uy equal to xi minus a by h, where Uy is the ith scaled deviation to the original deviation xi minus a, right? So we write like this, xi minus a equal to h times Ui, and we call this equation 1. So what you get? If you have a deviation from an arbitrary point A and your scaling factor is h, then you have like this, that xi minus a equal to h times Ui. Now, from equation 1, you have this. You just bring the a on the right hand side. Okay. Now, you sum up all the xi's and divide that sum by n, and this is on the left hand side. You do the same thing on the right hand side. You sum up all the a's and divide the sum by n, and here also you sum up all the h times ui's and divide that sum by n. Now, if you add all those xi's and divide that sum by n, then you will get the mean, that is x bar. Next, you add all the a's. Here the number of a's is n, so you add a n times and divide that sum by n, and you will get the a itself. Next, you bring this h out of this summation business because h has nothing to do with the summation. So you keep this ui inside the summation so that you can add the ui's and divide that sum by n, and you will get like this. X bar on the left hand side, you have this right hand side a plus h times this ui's added and divided by n will give you u bar. Now, xi minus x bar. Xi is a plus h ui. So you have written like this, a plus h ui minus x bar. X bar is here, a plus h u bar. So minus a minus h u bar, right? From this, you will get h ui minus h u bar. Next, h times ui minus u bar. And this is our equation 2. So you see that if you have a deviation from the mean, then it will give you h times ui minus u bar. That is the scaled deviation minus the mean of the scaled deviations, right? So finally, you will get this xi minus a, this is the equation 1, equal to h times ui. That means when you have deviation from any arbitrary point a and you have a scaling factor h, then you will have this equation, that is xi minus a equal to h times ui. Now this scaled deviation, that is the ui, is actually deviation from 0. So you can write like this, h equal to ui minus 0. So xi has a deviation from arbitrary point a will give you h times ui with a deviation from 0. And the second one, if you have a deviation xi from the mean, then you have h times ui minus u bar. I hope it's clear to you how a change in the origin and scale affect moments. Regarding this topic, if you have any question, you can write me in the comment box. In the next video, we'll talk about Shefford's corrections for moments.